Okay, we left off talking about hydrostatic equilibrium, and now I want to talk about thermal equilibrium. So, hydrostatic equilibrium was the equilibrium of the gas wanting to push out, balancing with pushing in. Well, because of this, the density is going to change within the sun. So, the sun's interior is very hot and it's made of all gas. So, that means the density, how much matter you have per area, is going to increase deeper in the sun. So the amount of the density is per volume. It's mass per volume. So how much stuff you have per volume. So as you go deeper into the sun, it's going to get more dense. So just think about it, it's more crowded in there. Okay, so the gas particles on the very outside of the sun in the atmosphere are spread out. Okay, they're spread out very thin, but as you get deep down in the center where those reactions are taking place, it's really crowded with all of those gas molecules. So as you get really crowded, those gas molecules are trying to bounce all around, right? Really crowded, they start hitting each other more and more and more. So the temperature increases. So as the gas particles have more room, they don't hit each other as much, okay, the temperature will decrease. So the temperature increases as we go closer to the center of the sun. But how that energy transfers, okay, how that heat transfers, there's a couple different methods. So thermal energy is generated in the core, and it has to transport out to the surface and then to us here on Earth. So how does it transfer? There's three methods of heat transfer in the sun. Well, just in general, okay? There's conduction, convection, and radiation. And the sun does all of these, but the conduction is not very effective. Convection and radiation are the most effective ways to transfer heat and to transfer energy within the sun and then out of the sun. So what are these three different types? Conduction is the movement of a heat on the atomic scale collisions. So this is when atoms literally touch each other. So you imagine putting your spoon into your hot coffee to stir in your sugar. Well, the spoon gets hot because the molecules of the spoon are bumping into each other and transferring that heat from the base of the spoon in the hot liquid up to the handle. That's conduction. The molecules have to actually touch each other. So the sun is a gas. So that means the gas particles aren't really close together. Now, I know I said they got closer in the center, but in general, there's still space between them. So the ability to touch each other and transfer heat that way is not very efficient within a gas, which is what the sun is. Instead, the sun uses convection and radiation. So convection is the bulk transfer of molecules by circulating fluids. So the best example of convection is in a pot of boiling water. At the bottom is the heat source, and the water is heated up, and so heat rises. Okay, it causes the water to move up, but then it expands out and it cools, and so then it sinks back down to the bottom. It continues to do this in what's called a convection cell, and this is a great method of heat transfer in liquids and gases, so very effective in the sun. And finally, we have radiation. Radiation is how we get heat and energy from our sun on Earth. So this is electromagnetic radiation, the transfer of heat. So individual photons are absorbed and re-emitted by atoms and electrons within our sun, and then that photon radiation gets to us, and it can travel without touching, okay, without a fluid, so it can travel through the vacuum of space. So please watch these videos on radiation and convection. They're posted on the Blackboard site as well, but here are the links here for you to watch. Please take the time to watch these. All right, so which one, you have a campfire sitting here, which way does the heat transfer from the campfire to your hands? Okay, so there's three different ways a fire can transfer heat to your hands. Radiation, convection, and conduction. Well, so which one in this case is radiation? So take a look, is it A, B, or C? Which is radiation? Okay, its radiation is here. So convection is happening by the air currents, okay, moving the heat through the air, and that's how you feel the heat. Conduction would be if you actually physically touch the fire, or in this case, the poker. And radiative heat is coming from those photons radiating out from the side. That's also how you get heat from radiative heaters. So where do these different elements take place within the sun? Well, we have the thermonuclear core, okay, that's where the thermonuclear reactions are happening. And that energy is radiated out in the radiative zone. And then we have a convective zone at the very top layer of the sun. And this is going to be important because the convection zone helps contribute to our sunspots and solar prominences. Okay, so go ahead and answer these concept questions. If you put a fire to help you understand thermal transfer of heat a little bit better. So you put a frying pan on your electric stove. How is heat transferred from the burner to the bottom of the pan? Your electric stove. Conduction. You're literally touching the pot to the heating element. Okay, so it's conduction. Not very effective in our sun. So how about you're cooking a pot of chicken noodle soup? And the heat is transferred from the burner to the pot, and then the heat is somehow transferred throughout the soup to make it boil. What type of heat transfer is this? Convection, okay? The transfer of molecules moving through gas and liquid. Very effective in the sun. And finally, how can we feel the heat generated by the sun? How does heat get to us from the sun? Radiation. Okay, it can transfer through a vacuum of space. Very effective in the sun as well. Okay, so I like these plots here because it shows you the surface of the sun, okay, from the center to the surface. Okay, center to the surface on each graph. And it looks, you can have a good idea looking at the luminosity, okay, the mass, the temperature, and the density. Okay, so notice that the density is going to increase at the center and decrease towards the edge. Same with the temperature. But of course, the mass, okay, as you get further to the surface, you're containing more of the mass. And same with the luminosity. So just a nice little interesting plots for you to see about the sun. Okay, so let's talk about the layers. Okay, the layers of the photosphere, or layers of the sun. So the photosphere is the surface of the sun. Okay, everything else is really gas and atmosphere that is really thin. So when we look at the sun, we're looking at the photosphere, that quote-unquote surface of the ball of gas. The lowest of the three layers of the sun's atmosphere are the corona, the chromosphere, and then we hit the photosphere. And everything below the photosphere we call the solar interior. So the temperature decreases as you go up within the photosphere. And so we also see something called a dark limb around the sun. See how the dark edge of the sun looks different than the bright center? Okay, that's something called limb darkening. And this is a result of how you look at the sun. So if you look at the sun straight on, okay, the observer is looking at the center of the sun. Okay, the center of the sun's disk. So you're seeing the very hot, luminous base of the solar system. So it appears, of the solar system, of the photosphere of the sun. And so it appears very bright, white or yellow. But if you're looking at the edge, okay, you're looking through only part way to in the relatively cool photosphere compared to the full surface and center of the sun. So it looks a little bit darker. So that's how we get this limb darkening here. Okay, so you're looking straight on versus just through parts of the photosphere which are cooler than the center. These dark areas here are sunspots, and those are on the photosphere, on the surface of the sun. Now, in addition, the surface of the sun looks something like the Thing from Fantastic Four. Okay, his kind of his body, that rocky body. Well, this actually looks like the granulation within the sun's surface. So I really think the sun's surface looks like the Thing from Fantastic Four. So it looks kind of this granular appearance, okay, like this. Okay, this granular appearance of the surface of the sun is all due to convection. Okay, so it's hot and cool spots. So the cooler areas are dark and the hotter areas are bright. So let's take a look here. So the cooler areas are these dark regions and these hotter areas are brighter. So you're looking at how convection is moving through the photosphere of our sun. Okay, the hotter gas is rising and then cooling off and sinking towards the edges. So we see these dark edges surrounded by these hot center regions. So this is the surface of the sun, the photosphere. So why can we see a surface of the sun if it is just a ball of gas? Why don't we see right through it? This is a great question. What do you think? Okay, so those gas particles are packed very densely in the sun. Remember, the density increases as you go to the center. So we're not able to see through because it's so densely packed. So it is gas, but it's so much gas in such a small area relatively. Okay, sunspots. These are cooler regions on the sun. So they appear darker than the surface because they are physically cooler than the surrounding area of the sun. So these dark regions are actually one of the ways that we talk about our sun being active is because of sunspots. So we can monitor the changing of sunspots. So sunspots come and go as the surface features of the sun changes. And this actually happens on about an 11-year cycle. And sunspots are areas of cooler regions where the magnetic fields actually spin up and then go back down into the sun. And I'll show you this in a minute. So if you want to monitor your own sunspots, go to spaceweather.com and you can check out how many sunspots we have on the sun today. So I encourage you to do that. Okay, so here's the blown up view of a sunspot. Just how we talked about eclipses, there's a dark region and then a lighter region called the umbra and the penumbra. Same thing occurs on sunspots. And sunspots are going to move across the sun. So here's daily motion of these sunspots spinning around our sun. Okay, so sunspots interact with the magnetic field. So the sun's magnetic field gets all twisted up and it creates these prominences as it goes from sunspot to sunspot. And every 11 years, the polarity of the sun will switch and the magnetic fields will untie themselves and then start the process again. So as the sun is spinning, these magnetic fields, they all twisted up, and that's where we see these prominences or these sunspots occur. So here's the layers of the sun. We have our chromosphere, and then within the chromosphere, we're going to see things called spikles. Then we have the corona, the outer layer, and then we have prominences that you'll see that can go all the way up into the corona. So here's our chromosphere, and here's these spikles. Okay, so this chromosphere here, we're blocking out the sun so we can see it. The corona, when we have a solar eclipse, you're able to see the very diffuse gas forming the atmosphere of the sun. And then our prominences. Look how big these things are. They can be bigger than the size of the Earth. And these are coming out of these sunspots, okay, where those magnetic fields are twisted up, and they're taking the plasma and the gas within those magnetic field lines and arcing them up. Now, sometimes they can get so big that they can eject out, and that's when we have what's called a coronal mass ejection. And this contributes a lot to the material that interacts with our own magnetic field. And a lot of this is what creates the solar auroras on the northern and southern poles of the sun, or of the Earth. So the sun is actively changing. Okay, so over the years we can notice how the solar cycles go lower and higher, meaning that we have more active times and less active times. And this is part of that 11-year cycle of the sun. Now it really is like 22 years because you count both low activity and then high activity again to double up to be 22 years. Now I know I flew through that, so please watch the next video given by Crash Course Astronomy and read your textbook.